We want to do an analysis of viscous flow through circular conduits. But to do that, it's really going to be helpful if we go back and do a quick review of some of the background material of how we got here. All right, so we're going to start with going back to the Buckingham pipe. So this analysis will give us two important results, and these apply directly to the flow of viscous fluids through circular conduits. The first of these terms is the Reynolds number, which we defined as the ratio of inertial forces to viscous forces. We define it by writing the density times the velocity times the diameter of the pipe divided by the dynamic viscosity. We can also then divide density by the dynamic viscosity by density and write it in terms of the kinematic viscosity, where v is the average flow velocity. And we get that by looking at the volumetric flow rate, which is Q divided by A, where A in this case is pi over 4d squared, where d is the diameter of the pipe. The second term that we get, and it's from example 8.4 in the text, is this relationship between the change in pressure, or the pressure drop in the pipe, and we say that that's going to be equal to the density times the velocity squared and some unspecified function of three dimensionless parameters. In this case, the Reynolds number, the length that we're looking at divided by the diameter of the pipe, and epsilon, which is the surface roughness, divided by the diameter of the pipe. And now we'll use these two results as we continue our analysis, where we want to end up with the equations from Chapter 10 that will allow us to analyze and design pipe flow. The next element that we need to introduce into our discussion is the Bernoulli equation, and this was developed in Chapter 5. Remember now, it was obtained by considering the forces acting on a small fluid element. Right, so we drew that little element, and then we considered forces that were normal to this little element. Those are our pressure forces. And then we also looked at body forces, but we restricted those body forces to the weight of the object itself, or the particle. In this case, viscous effects are not considered. So finally, the flow was also considered to be restricted to being along a single streamline. So there were restrictions on this. And what we ended up with was the equation where P1 over gamma plus V1 squared over 2G plus Z1 would then equal P2 over gamma plus V2 squared over G plus Z squared. And in this form, each of these terms are now in units of length. So we either would say the pressure, or the whole equation would have units of length, or of meters or feet. And we're going to now utilize this, or remember what this is, when we are now discussing and thinking about the energy equation, which will include the viscous losses. So the next element that we need to consider to put all our stuff together is the control volume analysis that we used, and that introduced this concept of the Reynolds transport theorem. And together, this was used to develop expressions for conservation of mass and linear momentum. Now, we can put the right-hand side of the equations aside for a second, but the left-hand side of these equations were used to describe the time rate of change of the fluid property that was part of the system. And what we end up with for conservation of mass was that the time rate of change of the total mass of the system is equal to 0, which of course, that's what we refer to as continuity. And for linear momentum, we have the time rate of change of the total momentum of the system equaled the sum of the forces acting on the contents of the control volume. So basically, if the system of mass was going to have its momentum change, there had to be a set of external forces, and those acted on the control volume at the exact instant that the mass of the system was coincident with the control volume. The next piece in our puzzle is the actual energy equation, and this was developed in section 5.5 of the text. So the energy equation will end up looking like the Bernoulli equation, but the analysis that we use to get there is via the control volume analysis, in which we have to use the Reynolds transport theorem. We did this for conservation of mass and the linear momentum equation. Now we can skip most of the details, but there are some important concepts. And to get there, let's take a look at the way we developed the other two equations. So for conservation of mass, we let the x-tensive property equal m, and the n-tensive property is m divided by m, which equaled 1. The same thing for the linear momentum equation. The x-tensive property is m times v, the momentum, and the intensive property is divided that by the mass, so it's just the velocity vector. Now for the energy equation, we have the total energy of the system, which is capital E. So we divide that through by mass, and we end up with the symbol of little e. Now, little e is the total energy of the fluid per unit mass. And it has three components. The first one is 1/2 v squared. Again, if you put m in there, it'd be 1/2 mv squared. So it's the kinetic energy per unit mass. The second term is gravitational potential energy, so mgh, again, per unit mass. And then we have this term u, and that's the internal energy of the fluid, something that we don't often talk about, but it's the molecular motion of the particles that make up the fluid. So what it really comes down to is that this is the heat of the system, what we would consider heat. So now, utilizing that, or that intensive property now E, we can use the Reynolds transport theorem to write the control volume form of the energy equation, which can be written as the total time rate of change of the energy within the system will equal ddt of the integral of the control volume of the intensive version of energy, little e, times rho times dv, the volume, plus the integral of the over the control surface of E times the density times the dot product of the actual velocity dot dA. So the rest of the details of taking this form of the energy equation and converting it to the form of the equation that applies to pipe flow are in the textbook. And since we have pipe flow, we're only going to have one inlet and one outlet. But it's the left-hand side of the equation that I want to dwell on in our next section, because what we want to know are what are the elements that will cause the change of energy within the system. And what we're going to find out is that, yes, there are external forces or external elements that we're going to call as being pumps and turbines, but it's going to be the right-hand side of the equation that will also account for the viscous losses. So we'll look at that in our next slide. So now, as with other applications of the Reynolds transport theorem, it's necessary to determine the form of the right-hand side of this equation. So we take a look at the time rate of change of the total energy of the system. And from thermodynamics, we can recognize that the change of the energy of a system that is composed of mass, or a mass system, requires the exchange of both thermal energy, or as I've written here, thermal energy and or work. So thermal energy is going to be heat coming into or out of the control surface. And then we have three types of work that we need to consider. The first is PDV work, which you should be familiar with from thermodynamics. And this is how pressure now comes into the energy equation. We have another term, W dot sub S, that is shaft work. So that is going to account for our pumps and our turbines. The last term is shear work, and it's a term that we include even though it's zero. And it stated that the viscosity of any real fluid will cause shear stress to develop tangent to the control volume's inner surface. Because of the no-slip condition on a fixed control surface, no work can be done by the shear stress since it does not move along the surface. So this term is included for completeness in the analysis, but since we are going to be considering pipe flow with one inlet and one outlet, it does not have any effect. The other term that we will not be looking at is the thermal energy, since we're not going to be considering the transfer of heat across the boundaries of the pipe. That is something you'll be looking at next semester in heat transfer. So what we're left with is the flow work and the shaft work, and we will look at that now in the next step. Our goal now is to recast the control volume form of the energy equation such that it applies specifically to pipe flow. So for pipe flow, the following conditions are going to apply. We're going to assume steady flow, the fluid will be incompressible, there will be one inlet and one outlet, and there's going to be no heat transfer across the control surface. The control surface being the wall of the pipe. And now under these conditions, the heat equation is going to become, on the left-hand side, there's going to be the work in term, right? There's no Q dot term because we're not having heat transfer across the control surface. And that's going to equal just the control surface term, not the control volume term, because that's only applicable for non-steady state cases. Here you see that we've now expanded out little e to include the kinetic energy term, the potential energy term, and the internal energy term. And those terms are then multiplied by rho v dot dA. All right, so it's important to note that this equation is the time rate of change of the energy, and the units of each term are joules per second, also known as watts. If we work in the English units or the FPS system, we're going to have foot-pounds per second. Foot-pounds is work, the rate is per second. And you'll also see it sometimes used as horsepower, where 1 horsepower is equal to 550 foot-pounds per second. So we can expand out the left-hand side, which is W dot in term, and we'll see that that includes the work energy of the pump minus the work energy of a turbine plus the flow work per unit time. Now the flow work per unit time will obtain a form that is minus the integral over the control surface of P times V dot dA. Now we have a figure over here that kind of explains that. The pressure is acting on the left-hand side of the control surface, so the inlet, and the work is P dV, so pressure times the volume, and it's a rate, so it's times d or divided by dt. And we can say that that's the pressure times dA, and then we have this incremental distance ds, so ds times dt. ds gives me the volume, ds dt is the velocity, so that gives me the pv dot dA term. And this negative sign shows up to keep everything pointing in the right direction. So we end up with the left-hand side, W dot N equals this expression for the flow work per unit time plus energy into the control volume via a pump and energy taken out of the control volume via a turbine. All right, so now we can put the two pieces of the energy equation back together again. So on the left-hand side, we have the terms that will cause the time rate of change of energy within the control volume, and we term these as work. So we have flow work, pump work, and turbine work, and that is going to equal on the right-hand side the change of the energy of the fluid within the control volume. And the energy terms here are the kinetic energy, gravitational potential energy, and the internal energy. So now what we need to do is go from this form to the eventual form we're looking for that will allow us to analyze pipe flow problems. And to do this, we have a couple more steps that I'm going to skip. So the first thing we need to do is we need to combine like terms so that integral over the control surface of the pressure term is going to go to the right-hand side. We want to set the control surface instead of integrating over the control surface. Now we'll have one inlet and one outlet. Then we're going to do a couple, right, put it in quotes, tricks. We're going to divide both sides by the mass flow rate, which is rho AV. We'll note that there is, of course, a change of units when we do this. And then we'll also divide by G, and that will allow us to express the equation in terms of pressure head. And then the last thing, well, we're going to note is that we're going to have the U2, the internal energy at the outlet of a pipe, is going to be greater than the internal energy at the inlet. And this is due to the conversion of useful energy into internal energy or heat due to viscous effects. And we'll term this as a loss term. And once we've done all of that, we arrive at equation 514, which is nicely broken up because it explains the terms that occur only at the open control surfaces and the pump, turbine, and loss terms that, of course, occur within the control volume. The last step in this process is to determine an analytical expression for the loss term HL. We'll be able to do this explicitly for laminar flows, and we'll have to use dimensional analysis for flows that are turbulent, and we'll cover that in our next slide.